This is a recording for the notes for 2-6 for Tuesday 10/22. And there was one application on 2-5 and then the two problems that we had skipped over. And if you want to look at those 3 problems, you can go to my YOLA site and look at that. Otherwise, I'm just going to move on to section 2.6, and that is rational functions. Essentially, this is when we have one polynomial divided by another polynomial, and that gives us rational functions. So just a reminder, you've looked at asymptotes before in your life, and when we have a vertical asymptote, the graph can't cross that because it's an undefined value. However, horizontal and slant asymptotes, those will be the other asymptotes that we're looking at in this lesson, deal with end behavior. So the graph can cross horizontal and slant asymptotes. Generally, if they are going to cross, it's going to be closer to the y-axis as we go. So I have a lot of notes to go through with you, and I'll talk about that at the beginning of the hour on Wednesday. But what I'd like to do is, as you're watching this, if you can't keep up with the slides, maybe go back to my YOLA site and copy the notes from there. And I'll try to put this recording on there. If not today before I leave, then tomorrow after I get back. But you should have access to all of that as well. So here is the objectives for this lesson. We want to find the domains of rational functions, find the vertical and horizontal asymptotes of graphs of rational functions, sketch the graphs of rational functions, sketch the graphs of rational functions that have slant asymptotes, and use rational functions to model and solve real-life problems. So we are going to use lots of things from our previous section as well. I have some of these notes kind of pre-set up, so I will be just reading through a few things as we go. You should maybe write down the underlined information. A rational function is the quotient of 2 polynomial functions, and it can be written f of x equals n of x over d of x. When you kind of think of n of x as the numerator function and d of x as the denominator function. Where n of x and d of x are both polynomials, d of x is not a 0 polynomial because we can't divide by 0. In general, the domain is all real numbers except x values that make the denominator equal to 0. And so a lot of times we're going to be looking at the graphical behavior near the x values excluded from the domain as we go through that. So we're going to start with this function that we should be familiar with, finding the domain of f of x equals 1 over x, and discuss the behavior near any excluded x values as we look. So this is number 1. F of x equals 1 over x. And so as I examine this, it is undefined when x equals 0. So the domain is D, and set builder notation is a set of all x such that x does not equal 0 and x is an element of the real numbers. If we wanted to give that an interval notation, we could say it goes from -infinity to 0, union with 0 to +infinity. So that's kind of our trouble spot, is where that is going to be equal to 0. So to find behavior near that behavior near x equals 0, we look at values close to x equals 0 and see what f of x looks like. Or y looks like. So we're going to make a table of values, and so I'll just write that, make a table of values. And we want to look at when x values get close to 0. And so I'm not going to do something that I can just find an easy numerical table of values for, but certainly I can use that table feature to find some of these values. So I'm going to make an xy table, and I'm going to have x be -1, then -0.5, then -0.1, then -0.01, and then -0.001, and then I'll have kind of my 0 placeholder. So notice I'm getting very, very close to 0 for my x values, and then I'll go positive from very close. I'll go 0.001, 0.01, 0.05, and then 0.1. So I'm not even using exactly the same values as I go. And certainly we're all capable of making this table of values. And I'm just going to kind of remind you what this is. So y equals 1 over x. So 1 over -1 is -1. And then 1 over -1/2. I'll just write it as a fraction. When I invert and multiply, it'll be -2. And then this one will be -10, -100, -1,000. And then we get an error message if we try to look at our table of values for that one. And then at 0.001, we get 1,000. Then at 0.01, we get 100. At 0.05, we get 20, and at 0.1, we get 10. So I just put a variety of values, then I want to kind of look at what's happening. So when I look at this, and maybe I am going to, oops, let me see if, oh, no. When I look at this, I'm going to look at what's happening to my x values and what's happening to my y values. And so let me pause this just a moment. Okay, I just paused this to give myself a little bit of space above the table and below the table. So now I'm just going to kind of examine what's happening. So I want to look what happens kind of as I get close to this value of 0 that's undefined. And so as I look along this table, my x values, x gets closer to 0, kind of from the left, And as that's happening, I want to kind of look at what's happening to my y values in that same kind of place. So my y values are decreasing without bound, decreasing without bound. Oh, I didn't spell bound very well. Without bound. And so f of x goes to -infinity as we look at that. And then we'll talk about that in just a minute. But first, we'll also look at what happens on this other side. And so here, from the right, x, as I'm looking at these x values kind of going from the right towards 0, x gets closer to 0. From the right. And we'll kind of talk about what that means, the right and the left here as we go. And then let me just kind of find a little different color to use here. And then what's happening to y as we go through here. And now notice that the y values go to positive infinity. And you would see if you try point 0.00001 that gets bigger and bigger. So here's kind of what's happening as x gets close to 0 from either the left or the right. And so we have a way of referring to that. So I'm going to say as x approaches 0 from the left, and I'm going to call that 0 with like a little negative sign above it, comma, f of x decreases without bound, decreases without bound. So it goes to negative infinity. And likewise, as x approaches 0 from the right, and so we'll say that's a 0 with a little plus sign, then f of x increases without bound. So it goes to positive infinity. Now, we want to say that a little more succinctly or with less words. So we can say it this way. F of x goes to negative infinity as x, I still can't write as x goes to 0 from the left, and we can say f of x goes to positive infinity as x goes to 0 from the right. And that means that if it's going to kind of negative infinity and positive infinity, that means that at x equals 0, there's going to be a vertical asymptote. And so this means that the line x equals 0 is a vertical asymptote. Vertical asymptote. And you can also see, I'll put the graph on, just draw a little graph of this. And we're familiar with this a little bit. 1, 2, 3. I'll just kind of quickly do a little sketch of this graph. And we know that this graph looks like it goes through 1, 1, and it goes through -1, -1. And we know that it goes kind of like this. And we know that it goes kind of like that. I'm just going to maybe slide it in a little bit. And so that tells us that this x equals 0 is an asymptote. Is an asymptote. And we also have here, and I'll use kind of maybe, I'll use a little darker color. We also have, if we want to put this one in, that y equals 0 is an asymptote also. So that's what we're going to do is we're going to examine now things that have vertical and horizontal asymptotes. So here's our next slide. And now we're going to look at vertical and horizontal asymptotes. So as we looked at that behavior near zero, we found that these things happened. F of x goes to negative infinity as x goes to zero from the negative side or from the left, and f of x goes to infinity as x goes to zero from the positive side. And so here's just another little picture of that and just a reminder of those asymptotes. And we kind of know that that has that horizontal asymptote as well. So now we want to look at how we're going to figure out where these horizontal and vertical asymptotes are. So the definition of vertical and horizontal asymptotes, the line x equals a is a vertical asymptote of f when f of x goes to infinity or f of x goes to negative infinity as x goes to a from either the right or the left. And then our kind of other thing that we're going to have is the line y equals b is a horizontal asymptote of the graph when f of x goes to b, some value. It may be 0 sometimes, it may be a numerical value as x goes to positive infinity or x goes to negative infinity. And so that the important thing for that horizontal asymptote is that it is talking about end behavior, and as the graph is near the y-axis, it can cross that asymptote because this is just talking about eventually as x goes to positive infinity or negative infinity. And so for a horizontal asymptote. So just a little different than a vertical one. Then excuse me. This shows several vertical and horizontal asymptotes of 3 rational functions. So you can just, for now, just kind of look at those. If you want to jot one down, you can. And I have one on the next slide as well. So here's the horizontal and vertical asymptotes. If you want to write those down, you can kind of find that on the YOLA site as well. I will say this, near the end of the year, we will be studying hyperbolas, and you already have this f of x equals 1 over x in your notes. There's another one there that says 2x plus 1 over x plus 1, and you should put at least one of those in your notes. If you want to use the one you already have, that's fine, but just label it as a hyperbola. And at this moment, that's all we're saying, is it is a hyperbola. We're not really going to say more about it. And then we need to know how to find these vertical and horizontal asymptotes. And this is a lot more complicated looking than it is in practice, but we'll go over it. And you should write this information in your notes. If you can't right now, it will be on the YOLA site. So vertical and horizontal asymptotes of a rational function, let f be the rational function f of x equals n of x over d of x, which equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0 all over d of x, which is b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus dot 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 plus b sub 1 x plus b sub 0, where n of x and d of x have no common factors. Then the graph of f has a vertical asymptote at any of the zeros of the denominator. So if we set the denominator equal to 0, then that's how we find our vertical asymptotes. Vertical asymptotes when the denominator is equal to 0. And the graph, number 2 is the graph has one or no horizontal asymptote determined by comparing the degrees of the polynomials. And then this says when n is less than m, then y equals 0 is a horizontal asymptote. And the way that I like to say that is if it's x to the lower power over x to a higher power, then y equals 0 is the asymptote for that one. And then the next one is when n equals m, then y equals a sub n over b sub n. The ratio of the leading coefficients is the horizontal asymptote. So for this one, we're looking at this piece over this piece. And I'll just go kind of over to the side here a little bit. And so if this is a sub n x to the same over b sub m x to the same, then the asymptote is at y equals a sub n over b sub m. And that is the coefficients of those two leading coefficients as we go. And then if n is greater than m, so it's a higher power over a lower power, then there's no horizontal. So if it's x to the higher over x to the lower, there's no horizontal asymptote. So that's kind of just the little way that I look at that. So generally, I find any vertical asymptotes by setting that denominator equal to 0 and finding those zeros. And then just kind of a comparison of what's happening for those powers to see if there is a horizontal asymptote as we look at that. So the next thing is just to kind of look at a few problems where we're going to find the horizontal and the vertical asymptotes, and just by kind of examining these functions as we go. And I'm just going to get rid of this part B. I have it on a different slide, and so it's a little hard to see anyway. So here's our first problem, is find all vertical and horizontal asymptotes for the graph of the function. So for vertical asymptotes, we set the denominator equal to 0, denominator equals 0. And so in that case, it's this stuff. So we just go x squared minus 1 equals 0. And we factor that, x plus 1, x minus 1 equals 0. So x equals negative 1. And x equals positive 1. So those are our two vertical asymptotes. Then to find our horizontal asymptotes, then we have to look at kind of these powers. And so we're looking at the leading coefficients. They happen to be they have to be happen to be ax to the same over bx to the same. So the asymptote is going to be at y equals a over b. And so I'm kind of comparing these leading coefficients. I'll kind of slide this up a little bit. And this is 2x squared over 1x squared. I don't really care about the rest of any polynomials that I would have after that when I'm just looking for the horizontal asymptote. Since those powers are the same, it's going to be y equals 2 over 1 or 2. So we're not going to graph this, but we are just going to kind of remind ourselves of where those asymptotes would be if we graph this. And so I'll just put a couple numbers on here. 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. So if I were going to pursue this problem, which I'm not, I just wanted to find where the asymptotes are. I have a vertical asymptote at x equals positive 1 or negative 1 and positive 1. So that means I have one there and I have one there. And then I have a horizontal asymptote at y equals 2. So that kind of divides my quadrant or my coordinate plane into like 6 little compartments, and so then I could kind of move on and graph from there. Then the next one is this letter B, and same thing. We're going to find the vertical and horizontal asymptotes. So for the vertical asymptotes, we just set the denominator equal to 0. So that is x squared minus x minus 6. And so we set it equal to 0. We'll factor that That one factors into x minus 3 and x plus 2. I'm gonna maybe write that factorization up here as well, because there's something that's actually gonna also happen there, and I want to kind of note that. So this factored into x minus 3 and x plus 2. So I do have to be careful because there aren't going to be two vertical asymptotes, and I have to kind of talk about that as I go. And then this numerator, I'm going to factor that as well. It really won't have any bearing on my asymptotes, except watch this. When I factor that numerator, it will factor into x minus 1 and x plus 2. And do you notice that these two are common factors? I'll use that kind of magic pen, and I am going to circle it. These two are the common factors, and kind of as we read through things, we don't want, we have to have things that are not common factors, and so that means there won't be an asymptote at x equals -2, but it is still undefined at x equals -2, but what we'll have there is a hole. And so this reduces to x minus 1 over x minus 3. Since this is a common factor, that means at x equals -2, there's a hole, not an asymptote. And so that's something that we want to be careful of. We still have that x cannot equal -2 and x cannot equal +3. Those are still undefined values, but in this case, at x equals -2, there's going to be a hole instead of an asymptote. Instead of an asymptote. And the reason being is that it was a common factor. And it can be kind of distributed or canceled off as we go. But at x equals x equals 3, x minus 3 equals 0. At x equals 3, that will be a vertical asymptote. So something to be careful of in the vertical asymptotes. Then horizontal asymptotes, we'll look at that also, horizontal asymptotes. And in this case, I'm going to go back to that original problem, and I'm going to compare those leading coefficients. So this is 1 over x squared and 1 over x squared. And this is ax to the same over bx to the same. And when that happens, then it's just going to be that ratio of the coefficients. So y equals 1 over 1 or y equals 1. And so that's our horizontal asymptote. So again, we're not going to graph this, but we're going to kind of just give ourselves a little sense of what this looks like. 1, 2. And so here's what's happening for this problem. At x equals 3, there's a vertical asymptote. At y equals 1, there's a horizontal asymptote. And then somewhere along here, when x equals -2, there's going to be a hole. And kind of to figure out where that hole is, I can in my head think about putting in a -2 here and a -2 there, and that'll be -3 over -3 over -5, so it'll be 3/5. So someplace along here is going to be a hole. And right now, I don't have to really know where that hole is. I'll just kind of put it here and say that I could kind of, I know it's somewhere along here. And as I kind of figured it out, I think it's someplace along there. But I don't have to know that right at this moment as I go through that. Then the next thing we want to do is find the asymptotes and then also graph this as we go. and oh no, just another one that we're just finding the asymptotes. So here's our next one, and these are also the same power. So the first thing I'll do is I will factor that denominator, and you notice from that last one, factoring that numerator can be a good idea as well. So this denominator will be x plus 1 and x plus 3. In the numerator, I maybe have to have 3x and x. And I need to get a kind of a 6 and a 7. And so I think if I put a 2 here and a 3 there, that'll give me 2x and 9x. So the plus 9 and the minus 2 will give me 7x as a middle term. And again on this one, that one will reduce. So I have 3x minus 2 over x plus 1. And for this one, I have a vertical asymptote. When a vertical asymptote when x equals -1, I have a hole at x equals -3, and a horizontal asymptote. These coefficients are the same, and notice the same thing happens in my reduced polynomial as well. They continue to be the same, and so y equals 3 over 1 or y equals 3 is the horizontal asymptote as well. So that's kind of finding the asymptotes. Once we find the asymptotes, then we want to use both the zeros and the asymptotes to be able to graph that function overall. And so this is sketching the graph of a rational function. Sketching the graph of a rational function. So here are the guidelines for sketching the graphs of rational functions. And I will kind of go over this with you, and I just have it also on the next slide as we go. So the guidelines are to do the following. And so we kind of already know how to do all of these pieces. And so the first thing we do is simplify if possible. And then the second thing we do is find and plot y-intercepts. So find and plot the y-intercept by finding f of 0. And then the third thing we do is we find the zeros, and those are by setting the numerator equal to 0, and we find the x-intercepts. So that's kind of our first thing that we do, first things that we do. And then the next step is to find when the denominator is 0, zeros of the denominator, and that will give us vertical asymptotes or sometimes holes. And then we find the horizontal asymptotes, and that is noting the powers of those two things as we go. And then our last thing is we set up an interval table. So I'm going to put set up interval table. And when we do that, we are looking at zeros sometimes. So we'll look at those. Sometimes we're looking at where those asymptotes are, and that's how we kind of get that interval table that we're going to need. And then our last thing we do is we find some things in those intervals as well, and then we make that smooth curve as we look at that. And the only thing I have additionally on this one is I kind of went through if it's x to the low over x to the high, there's a horizontal asymptote at y equals 0. If it's x to the same over x to the same, it's a over b. If x to the higher over x to the lower, there is none as we look at that. So the concept of test intervals is something that we're going to look at, and I think we looked at some test intervals before 4. And we're going to use the fact that a rational function can change signs only at its 0 or undefined values, and between any two consecutive zeros, the numerator and the denominator must be entirely positive or negative as we go. That means that when put in order, the zeros of the numerator and denominator divide our number line into some test intervals that we can choose representative values for. I am going to tell you that I am not going to probably get through with this lesson today, and so I will be finishing it tomorrow. We might have to reevaluate kind of our testing schedule tomorrow in class, but I will continue on, and I think I'm going to try to do at least this problem. So the first thing is the domain. And the domain is found by excluding when the denominator is 0. So the domain is all real numbers except x equals 2. And so we can give that as an interval if we want. Then we'll find next the y-intercept is when x is 0. And so when x is 0, I get y equals 3 over -2. And so -3/2. The x-intercept would be when that numerator is equal to 0. And since it's the number 3, that's just not going to happen. So there's none for the x-intercept. There's none. And then for this one, we'll have to find those asymptotes as we go. And so let me get ready to do that. The bell rang for my next class, so I'm just going to finish up this problem. So our vertical asymptote is when that denominator is equal to 0. So that gives us a vertical asymptote at x equals 0. Our horizontal asymptote for this one, we can see that this is 3 is like 3x to the 0 over x to the 1. So this is x to the lower over x to the higher. And that means that our horizontal asymptote is going to be at y equals 0. So first thing I'm going to do is kind of just plot some of those points on here to kind of get what I have. I have this point of 0, -3/2, so that's -1.5. That's going to be right about there. I have a vertical asymptote at x equals 2. And I have a horizontal asymptote at y equals 0. And so then that divides my axis into really just 2 intervals. So the first interval goes from -∞ all the way to this value of x equals 2, where it's undefined. And then my second interval goes from 2 to +∞. So let me get rid of that a minute. And there we go. And so that gives me this test interval, intervals, and x and y values from -∞ to 2 and from 2 to infinity. In this one, it's pretty straightforward. So I'm just going to try a couple of values. Oops. I'll try a value when x equals -4, and when x equals 3. I might even try 8, a second value. For this one, I get -0.5. For this one, I get 3. For this one, I get 1/2. So I'll plot those points at -4. 1, 2, 3, 4. I get -1/2. At 3, I get 3. And at 8, I get 1/2. As we look at that, and oops, Let me fix that asymptote a little bit over there. And then I just know that I'm going to have a smooth curve in those two intervals. So I'll just sketch in my graph here, and I will sketch in my graph there. And that is this problem. Our next one is this one, and we will look at that one tomorrow.